everyone and welcome to the Funtastic Academy. We are going to continue this mini-series on computer memory by talking about hard disk drives. For a long time, hard disk drives were the most common way of storing memory on computers. Recently, they've sort of been phased out in the place of solid-state drives, SSDs, the more common tool. But they're still pretty common, and especially common used in servers where they were used for a long time. And the manner in which they work is quite amazing. So we thought that it would be quite interesting to package it into a short 10-minute video for you all. But first, the quiz question. From last episode, we asked what is the equivalent of DRAM that is used in a GPU? The answer is VRAM. VRAM, or Video Random Access Memory, is essentially the same as DRAM, except that instead of being directly connected to the CPU, it's connected to the GPU, which allows it to do much faster parallel processing. So now, let's dive, or should we say drive in, to hard disk drive technology. A hard disk drive, as the name suggests, is made up of a disk, or in new models, multiple disks. This is mainly made up of aluminum, but the working surface that actually stores the data is made out of an alloy of cobalt, chromium, and tantalum. When the hard drive is operational, this disk can rotate at 7,200 rotations per minute. That's 120 times a second. Extremely fast. Now, the reason it rotates is so that the arm of the hard drive that does the actual reading and writing can easily access any part of the disk at any time. But how does it make sure the arm can stay close enough to the disk to read it without damaging the disk? Well, it turns out that when the disk is spinning fast enough, it actually makes an aerodynamic lifting force that pushes the arm slightly above. This is only a force of around 10 to 20 nanometers upwards on the arm. So the arm can only move into place when the disk is at its top speed. If it's slowing down or the hard drive is off, the arm is moved to the side by these solenoids with neodymium magnets. Now, this disk is divided into sectors. They have lines which go concentrically around the disk, and they have sectors in them going around the disk. Each sector has an error-correcting part so that if the disk gets damaged, it can still be read properly. An address so that the arm knows what part of the disk it's reading at all times, and a preamble so that the reading part never gets mixed up on when it's on a 1 or 0. We'll explain how that can happen a bit later. Now, when you want to read a particular message, the drive simply spins into place. It will still continue rotating, so the arm needs to continuously scan that location on the drive, and once it's finished, it temporarily stores that into DRAM as a buffer before sending it out back into the system. Now, we'll cover how this reading and writing procedure happens and what's actually inside the arm that makes it function. This is a rough model of what on a microscopic scale a hard drive while it's reading or writing would look like. You can see that the arm's reading and writing mechanisms are just hovering over the disk by just a few nanometers. And what are these? They are pieces of the chromium cobalt tantalum alloy. Now, these arrows represent the fact that the alloy can be magnetized. It can either be magnetized with the north direction pointing up or with the south direction pointing up. So in two possible directions. And each of these directions stores a bit, a 1 or a 0. And that's how the hard drive stores its data. Now, for writing data, we have this coil right inside the write unit. When the hard drive is properly positioned, this coil can just output a magnetic force which properly realigns the magnetic field in a particular portion of the alloy. These alloys are separated into minuscule domains, each of which can be around 100 by 100 by 100 nanometers in size. In each of these domains can only have one magnetic direction at a time, which this coil magnetizes them towards. What about reading though? There's no real way to read whether there's a north magnetic direction or a south magnetic direction at a particular point. The metal will be attracted to it either way. So the solution is detecting the switches between directions. They provide a more powerful magnetic flux that can be read more easily by the read unit. So the way the preamble I mentioned works is just an alternating stream of ones and zeros, so that the drive arm reading unit knows exactly how many switches have taken place and where it's currently at a 1 or a 0. Then by detecting switches, it can do something like this. I know we're at a 1 here because of the preamble. There's a switch here, so this must be a 0, and another switch, so this also must be a 1. No switch, so this is a 1 again. It can continue tracking like this, continuously reading each bit out of a set piece of the hard drive domain. The way it detects these switches is using something called giant magnetoresistance or GMR. They have alternating layers of a magnetic and a non-magnetic material, and the property of giant magnetoresistance makes it so that when there's a magnetic field around the point that the read unit's at, the resistivity or how much electricity can pass through the material changes drastically, allowing for changes in magnetic flux to be detected. And this, simply put, is how a hard drive reads and writes data. So, to recap, in today's episode, we learned about hard disk drive or HDD technology and how it stores such a massive amount of data yet allows it to be read and written quite easily using the magnetic alignments of pieces of an alloy in a disk. Now, to end this video, I'd like to leave you on a simple quiz question. What company was the first to massively commercialize hard disk drives? Tell me the answer and I'll see you at the next episode of Electronics of the Funtastic Academy. Bye!